in long term, you will see that it's like it doesn't depend on our moves. I mean, in long run, it's like you will see as a probability distribution, some Gaussian distribution like this. So it's very interesting that ergodic theory is related to graph theory in random walk, spectral graph theory, dynamical systems, even group theory, and all of them are connected. And measure theory, functional analysis. So it's an amazing topic. This is my hobby, ergodic theory. And a Markov chain is ergodic. We call it ergodic if both irreducible and aperiodic. It is free to go to any state. There is no discontinuity. There is nothing wrong. You can go in a long run. You can go to any other state. So why should I talk about that? Because there is a nice theorem that says an ergodic Markov chain has unique stationary distribution. And we love the convergence of probability distributions in machine learning. So this is interesting. And by definition, we say that for any epsilon greater than 0, mixing time is the number of steps needed to get epsilon close to the stationary distribution pi. This is the mixing time. And for starting states, let's say that sigma x to be, for example, when we say 1, 0, 0, 0, 0, it means that starting at state 1 with high probability, I mean with absolute 100% probability. And so this is for example, an example of an initial distribution for a starting distribution. And the important concept in all random walks is that T of mix of epsilon. We call it mixing time. So the mixing time, epsilon mixing time, let's say, is just the minimum T such that for any x, we have sigma x pt is epsilon close. I mean, the total variation norm is epsilon close. So pi and epsilon t are epsilon close. They are very close to each other. So these two distributions are very, very close to each other. So we have some errors here, but they are very close. So the total variation of them is epsilon. And the total variation distance between two probability measures P and Q is just the supremum of P of A minus Q of A. And for example, if mu and v are two probability distribution, the total variation is just 1/2 mu of x minus nu of x. And for example, one of them has probability distribution 1, 0, 0, and the other one has probability distribution 0, 0.9, and 0.1. So what is the total variation? It becomes 1/2 because of this, and then 1 plus 0.9 plus 0.1, which is 1. So think of this as the error, the remaining effort that you need to do in order to get to your beautiful stationary distribution. And the observation is that pp is equal to pi. So think of it as an eigenvector. You see, we talk about eigenvector of Laplacian, eigenvalue of Laplacian, and there everything was lambda equal to 0 was the lowest eigenvalue. Now your eigenvalue is 1. You know, there is a scalar 1, it is hidden here. So lambda is 1, eigenvalue 1 with eigenvector pi. And all eigenvalues in absolute value are less than 1. And because all of the rows sum to 1. And mixing time depends on the spectral gap. I mean, difference between first and second largest eigenvalue. So remember, the spectrum sometimes goes something like this. And of course, it could be the other way. Here is near, then it goes longer. But so the mixing time depends on the difference, on this difference between 1 and between the first eigenvalue and the second largest eigenvalue. So mixing time is something like that. So there is an important theorem that says for an ergodic Markov chain, if 1 is equal to lambda 1, lambda 2, and this is your spectrum, be the eigenvalues, and if pi of mean is minimum of pi of x over all x, then T of mix of epsilon is upper bounded by 1 over 1 maximum lambda 2 lambda mean log of 1 over epsilon pi mean. And T mix of epsilon is lower bounded by lambda 2 1 minus maximum lambda 2 and lambda mean log of 1 over 2 epsilon. And what is important is that, first I should say that a Markov chain is reversible if there is a distribution pi such that pi of x, p of x and y is equal to pi and y, p of y and x. For example, if you remember that conductance, that you go out from S to S complement, this is S complement, there should not be a difference from going from S to S bar or from S bar to S. So that's why it is called reversible. So a coupling, a very important tools in all theory of random walk, coupling. So a coupling of distribution mu and v, I mean, always remember it is on a state space omega with probability distribution p, is a pair of random variables x and y. On the probability space, now it is like this, f and f. I mean, your filtration is f. And probability space this, and you have a probability. So the marginals coincide. I mean, the probability of x inside A is mu of A, and probability of y is inside A is nu of A, for any A that you imagine. Let me give you an example. For example, Bernoulli simplest example. Bernoulli of P, if it is mu, if the probability of heads, so probability P to be probability of heads is equal to 1. For example, if heads, let's say heads equal to 1, and for example, heads and tail is equal to 0, for example. So if P is, if nu is Bernoulli of Q with probability Q greater than P, number of heads, then we can define H mu of n to be number of heads in n tosses. And H nu of n is number of heads in n tosses. And the proposition is that the probability of H mu greater than K is less than probability of H nu of n greater than K. I mean, the proof is very simple. I just want to skip the proof and go to some more interesting things. There is a lemma that we need, is that the total variation of mu and v is upper bounded by infimum of probability of x is not y. And we skip the proof of that again. There is a lemma that says that mu minus v, the total variation, is infimum over couplings that I said, couplings x and y, of p of x is not y. So always we want to see the discrepancy. For example, mu is here, another distribution is here. For example, this is alpha, beta, and so you can see what is mu minus v. So a coupling. So we can define coupling of Markov chains with transition probability P is just a process, xt, yt. So process x, this is x of t. This is, for example, y of t. So if you know the stochastic processes and theory of stochastic processes such as Brownian motion, then you will appreciate these approaches more, and you will understand Doob theorem, martingale, supermartingales, and those interesting stuff that has some structure, some properties that is useful in proving things. For example, a simple random walk, as you know, you go from one state to the other. For example, you go from here with probability half, you go upward, you go down with probability half, you do nothing to move outside an interval. So what we can say is that we can claim that the probability, the distribution after t steps, starting from y, is less than the probability of x and 0. We can also define a very important measure, which is d of t, is the maximum. It says that how far you are, how close you are to stationary distribution. What is the worst value? So the maximum at each point in time, you can measure how close you are to your stationary distribution. And d bar of t is defined similarly, but here we start at two different points, x and y. So we can measure the total distribution, total variation. But the important things that we love from triangle inequality is that d of t, d bar is sandwiched between two factors. And the mixing time, t mixing time, is now related to, by definition, it is the minimum of t such that d of t is epsilon. So now we can easily define that. And the final theorem that I want to say is that if x and t and y and t be a coupling, we start by x and we start y by y. And tau star be the first time they meet. So, for example, here is my stochastic process x of t. Here is another stochastic process, but after that, for example, they are equal. So this is x and t. For example, this has been started from here. So after sometimes they meet each other, and therefore they coincide. For example, it's like a dynamical system. If you start from this, after some time, you can find the Lyapunov function, and you see you converge to this global minimum. And because it is, for example, a stable manifold, if you start at a very close to this initial condition, then your trajectory is almost the same. And then you converge to the original system. So these intuitions comes from many different disciplines, such as stochastic processes, control theory, and many related things in dynamical systems. So the theorem says that now the probability of x and 0, the difference between them, the total variation between them, is upper bounded by pxy tau star greater than t. And remember, tau star is the first time they meet. For example, tau star, this is the first time they meet. Now we are ready to relate all of these things, these mouthful theorems, with something that we know: conductance, Cheeger constant, escaping probability. All of these are the same things. So let me remind you from computer science, from math, from mathematics, any discipline that you like, that if pi of s is less than 1/2, the minimum of this, so you can interpret conductance as something probabilistic. So we say x is in S, but y is not in S. So pi of x, p of x and y, pi of s. So spectral gap related to mixing, as you remember, is sandwiched between phi 2 over 2 and 2 phi. Cheeger inequality. Everything is related. So, for example, if you have this interesting graph, and another interesting graph, this is another interesting graph, 0.4, for example, and it has a